Hello, everyone. Welcome to CPE 517-WS Digital and Computer System Architecture. This is part 1 of Lecture 8. Lecture 8 is the continuation of Lecture 7. It's mainly about how to introduce speculative execution to dynamic scheduling of Tomasolo's algorithm. Okay, let's get started. So first, some logistics. For this course, majority of the slides will be adopted from David Patterson, Sam Lapsky. All the credits goes to original authors, and all the errors are mine. Reordering and modifications have been made due to requirement. Speculation to greater instruction level parallelism. What do you mean by greater ILP or instruction level parallelism? Which means we overcome the control dependency by hardware speculation on the outcome of the branches and execute programs as if our guesses were correct. Speculation to fetch, issue, and execution of instruction as if the branch prediction were always correct. Dynamic scheduling only fetches and issues instruction. Essentially, a data flow execution model is the thing of speculative execution. Operations executed as soon as the operands are available. Speculation to greater instruction level parallelism. There are 3 components of hardware-based speculation. First, dynamic branch prediction to choose which instruction to execute. Second, speculation allows execution of instructions before control dependencies are resolved. This is the ability to undo effects of incorrectly speculated sequences. For example, if I take this bet and it's wrong, so I can undo it. Right? We use dynamic scheduling to deal with the scheduling of different combinations for basic blocks, like data dependencies, this kind of thing. Right? Adding speculation to Tomasolo's algorithm, we must separate the execution from allowing instruction to finish or commit to execution. Execution can be done, but commit is really reflecting the change to register file or the memory. This additional step is called instruction commit. So basically, previously we have instruction fetch, execution, and finish, right? Writing results. But right now we write the results and then we commit. So when we write the results, we allow other instructions to dynamically scheduling, while commit reflects the changes to the memory that is other people can see it. Right? When an instruction is no longer speculative, then we allow it to update the register file or the memory. If it's not, if it is under the speculation process, we have to hold it in ROB buffer. It requires additional set of buffers to hold the results of instructions that have finished execution but have not been committed. So we introduce the commit and execution. Right? This is called reorder buffer, or ROB is used to pass. This can also be used to pass the results among instructions that might be speculating. So we not only use the ROB to hold the instructions that finished but not commit, but also these results that hold there can provide values for other instructions that depends upon this instruction. So what is reorder buffer? In Tomasolo's algorithm, once the instruction writes its results, any subsequent issued instructions will find the results in register file. Well, with speculation, the register file is not updated until the instruction commits. That's what I'm saying. So previously, it's after the register file, then it's done. It's really reflected. But in speculation, we do have another buffer to hold those results. Until this instruction is not speculated, then we can commit the instruction. Thus, the ROB supplies the operands internally between the completion instruction execution and the instruction commit. ROB is a source of operands for instructions, just like the reservation station that provides the operands in Tomasolo's algorithm. So ROB pretty much covers all the registers that are being used in a reservation station. Each entry in ROB contains 4 fields. That is instruction type, destination, value, and whether it's ready. Instruction type, a branch instruction has no destination results, a store has a memory, or a register operation has a register destination, right? Destination, register number for loads and ALU operations or memory addresses where the instruction results should be written to. Value, this is for like a commit, right? So when you execute it, finish that, and then that specific updates to which destination or destinations. Value, the value of the instruction results until the instruction commits. Ready indicates whether the instruction has been completed, and the value is ready for other instructions. This instruction. Reorder buffer, okay. Let me stop here, copy the prior dynamic scheduling here to do a comparison, head-to-head comparison, okay. Okay, still the left side of this is the Tamasulu's algorithm, and the right side is the speculative execution hardware. So you can see here, pretty much the only difference we had here is the reorder buffer, right? And then we don't have a common data bus anymore because the common data bus also goes to the reorder buffer to read the data. And then we have this floating point operation queue here. And then floating point register. Reservation stations. Reservation stations are like the loader, adder, multiplier, and those kind of things, right? So you can pretty much say it's very similar, except to have a reorder buffer that holds the value of the not commuted instructions. We hold the instructions in FIFO order exactly as they issued. Basically, when you issue one instruction, we put that instruction in reorder buffer. Supplies operands to other instructions between execution, complete, and commit. More registers are like the reservation station. We tag results with ROB buffer number instead of reservation station, so that when instruction commits, the values at the head of ROB buffer are placed in the registers. As a result, it's easy to undo speculative instructions on mispredicted instructions or exceptions because it's in the order of the issue. So basically, whatever instructions after, if this instruction is mispredicted, whatever below it can be flushed. 4 steps of speculative execution. So as you can see here, these 3 are the Tamasulu's algorithm, right? So you have issue, you have execution, you have read results. Well, add this commit to the speculative Tamasulu's algorithm. Getting instruction from the, so for issue, it's getting instruction from the floating point operation queue. If reservation station and reorder buffer slot are free, issue instructions and send operands and reorder buffer number for destination. Execution, when both operands are ready, then we do execution. If not ready, watch the CDB for the results or watch the ROB. When both in register reservation station, we execute, check the read after write problem, which is the output anti-dependency. Sorry, true dependency. Read results, finish execution. Write on the common data bus to what awaiting function units. And reorder buffer, mark on the reservation station available. Commit, we update the registers with reorder buffer results. When instruction at the head of reorder buffer and results present, update registers with results and or store to the memory and remove the instruction from the reorder buffer. Mispredicted instructions are flush. Mispredicted branch flushes reorder buffer the entire thing. Sometimes we call that graduation. So this is a running example of the rewarder buffer-based speculative execution, right? So we have the rewarder buffer. It holds all the instructions. We've put the first instruction is this, second instruction, fourth, fifth. Any updates? Sorry. So the first instruction, second instruction, third instruction, fourth instruction, fifth, last instruction. Okay. Assuming it's the cycle 3, right? So what we have is these instructions are committed, and instructions are writing results, and this instruction is executing, and this instruction is writing result. So we have a destination. The results we got from here, we write to F6, we write to F2, write to F0, write to F8, write to F0, write to F6. This is the same as what we have here. These are the destinations. And the values are the values to this that are required to compute these destinations. Reservation station is the same as dynamic sketching of Tamasulo's algorithm. We have BJ, VQ, VK, QJ, QK, destination, memory address, and operand, opcode, whether it's busy. Register status is also the same, very similar as the Tamasulo's algorithm, except we have the reorder buffer entry. Right, so you can say which one is busy, which is not busy. Right. So speculation execution avoids memory hazards. This is very straightforward. For write after write and write after read hazards, they are eliminated by speculative execution because we have actual updates of the memory occurring in order. Like we do execution out of order, but we issue in order and commit in order. So whatever is before have to be committed first. So basically, when a store is at ahead of the ROB, and hence no earliest nodes or stores can still be pending. They must be finished. Read after write hazards through memory are maintained by two restrictions. This is a true dependency, right? So not allowing a load to initiate the second step of its execution if any active ROB entry occupied by a store has a destination field that matches the value of the field of the load. So basically, whatever the provider is the so you might ask, okay, why not I directly go there and fetch the value? The problem is maybe it's there's a misprediction, there's a speculative execution, right? So we need them to be committed. Maintaining the program order for the computation of an effective address of the load with respect to all earlier stores. So basically, for all those effective addresses, they have to be the same. Probably it could be, let's see, A plus 10 versus B plus 8. They might be the same, right? So this can be memory aliasing problem. These restrictions ensures that any load that accesses a memory location written by earlier store cannot be performed the memory access until the store has written the value, right? Okay, so the first one is not memory aliasing, maintaining the program order for the computation of an effective address of a load with respect to all earlier stores. So this is for computing the or resolving the memory aliasing because it calculates the effective address, like A plus 10 will get the address, or B plus 8 will also get an exact address. Okay. So for exceptions and interrupts, as what we mentioned earlier in Tomasolo's algorithm, it would be hard for them to handle this kind of things. But here, in this case, we can easily handle that because we have the commit, right? It's easy. We do in order completion and in order commit. If the speculation are wrong, we need to back up and restart the execution to the point. If there's an exception, it's the same, right? It's exactly the same as needed to do with preset exception. Exceptions are handled by not recognizing the exception until the instruction that caused it is ready to commit. If you speculated instruction resists an exception, the exception is recorded in ROB. Therefore, ROB is all new processes. Okay, this is it for this part. We're going to move on to the next part.